up guys, this is George Kamiti. Welcome back to our channel. We are still analyzing simple stresses and strains. And we got this question that says this: a concrete column of cross-sectional area 400 by 400 millimeters is reinforced by 4 longitudinal 50 millimeters diameter round steel bars placed at each corner of the column cross section. If the column carries a compressive load of 300 kilonewtons, determine 1. The loads carried by steel bars. 2. The compressive stresses produced in the concrete and steel bars. The Young's modulus of elasticity of steel is 15 times that of concrete. Now, we are going to begin with determining or calculating the area of the concrete as well as the area of steel. But for us to get the area of concrete, we are going to calculate the area of the column cross section. We subtract the area of the 4 steel bars, and we are going to remain with the area of concrete. So in this case, we are going to say this: cross-sectional area of the column. Cross-sectional area of the column will be 400 meters by 400 meters. It is a square cross-section. So 400 millimeters, we need to convert millimeters to meters. So that is 400 divided by 1,000, since 1 meter is equivalent to 1,000 millimeters. So 400 divided by 1,000, that's going to be 0.4 meters. We multiply by another 0.4 meters, and that is going to give us the area of the column to be 0.16 square meters. So that is the cross-sectional area of the column. Then the area of the steel, we have 4 steel bars, and in this case we are going to determine the area of the 4 steel bars. Now, the cross-sectional area of steel bars will be given by 4 times pi over 4 d squared, since we have 4 of them. And in this case, this is going to be 4 times pi over 4 times the diameter of steel is 50 millimeters. We convert it to meters. 50 divided by 1,000, that's going to be 0.05 meters. So 4 times pi over 4 times 0.05 square meters. And that is going to give us an area. Let me write it up here. And that's going to give us a cross-sectional area of 7.854 times 10 raised to the power of -3 square meters. So that is the cross-sectional area of the 4 steel bars. So to get the area of the concrete, that is the area of the area covered by concrete, we are going to take the cross-sectional area of the column. We subtract the cross-sectional area of the steel bars. And in this case, cross-sectional area of the column is 0.16 square meters. Therefore, that's going to be 0.16 minus area of the steel bars, 7.854 times 10 raised to the power of -3. And that is going to give us an area of 0.152 square meters. Therefore, that is the area of the concrete. Now, from compatibility equations, we know that the strain in steel bars, is equal to the strain in concrete, equals to strain in concrete. So this means that strain in the steel bars is equal to the strain in concrete. Now, from this relation or from this formula, Young's modulus of elasticity is given by the ratio of stress to that of strain. Now, when we make strain the subject, we are going to have strain is equals stress divided by the Young's modulus of elasticity. Now, in this case, the strain in steel will be given by stress in steel divided by the Young's modulus of elasticity of steel, which is equals to strain in concrete will be stress in concrete divided by the Young's modulus of elasticity of concrete. When we make stress in steel the subject, we are going to have stress in steel is equals Young's modulus of elasticity of steel over Young's modulus of elasticity of concrete times the stress in concrete. So that is when you make stress in steel the subject. Now, at this point we have been told this, the Young's modulus of elasticity of steel is 15 times that of concrete. So we are going to have this Young's modulus of steel is equals 15 times the Young's modulus of elasticity of concrete. So this means that the ratio of the Young's modulus of elasticity of steel to that of concrete will be equal to 15. So we are going to substitute this one here, and this will lead us to stress in steel is equals to ES over EC is 15. Therefore, that's going to be 15 stress in concrete. So this relation, we are going to use it in a few. Now, we also know this from compatibility equation that this total load subjected onto this column, that is the load of 300 kilonewtons, will be shared by the steel bars as well as the concrete. And therefore, we are going to have this. The load shared by the steel bars plus the load shared by the concrete will be equal to the total load subjected onto this column, that is the load of 300 kilonewtons. Now, from simple stresses and strains, we know that stress is given by load divided by cross-sectional area. So when you make load the subject, you are going to have load is equal to stress multiplied by cross-sectional area. So the load shared by steel bars will be given by stress in steel bars times cross-sectional area of steel bars plus the load shared by concrete will be stress in concrete times cross-sectional area of concrete, which will be equal to the total load subjected onto this column. And this one will be stress in steel is this 15 stress in concrete. Therefore, we substitute it there. 15 stress in concrete times the area of the steel bars, which is up here, that is 7.854 times 10 raised to the power of -3. We add these two, the stress in concrete multiplied by the cross-sectional area of concrete, which is 0.152. So times 0.152 is equals to, the total load is 300 kilonewtons. We convert it to newtons, that is 300 times 1,000, which is going to be 300,000 newtons. 300,000 newtons. Now, when we multiply 15 by 7.854, we are going to have 0.1178 multiplied by the stress in concrete plus 0.152 stress in concrete is equals to 300,000 newtons. 300,000 newtons. So when you add 0.1178 plus 0.152, that one will give you 0.2698 stress in concrete, which will be equal to 300,000. So to get the stress in concrete, we are going to divide both sides by 0.2698. This side again, divide it by 0.2698, and this will give us a stress in concrete of 1.112 times 10 raised to the power of 6 newtons per square meter. This one can also be rewritten as 1.112 mega newtons per square meter, since 1 meganewton is equivalent to 1 million newtons. So that is it. On the other hand, the stress in steel is equals to 15 multiplied by the stress in concrete, and the stress in concrete is 1.112 times 10 raised to the power of 6 newtons per square meter. So when you multiply 15 times 1.112 times 10 raised to the power of 6, that is going to give us a stress in steel, a stress of 16.678 times 10 raised to the power of 6 newtons per square meter. So this one can also be rewritten as 16.678 meganewtons per square meter. So those are the stresses in both concrete and steel, as well as steel. So you have already answered that, the question part 2. Now, the other question is, we determine the loads carried by the steel bars. So PS, the loads carried by the steel bars will be given by stress produced in the steel bars multiplied by the cross-sectional area of steel. And this is going to be, the stress in steel is 16.678 times 10 raised to the power of 6 times cross-sectional area of steel, that is 7.854 times 10 raised to the power of -3 square meter. So this is going to give you a load of 130,992.18 newtons. So in kilonewtons, the load in steel is going to be, divide this by 1,000, that is going to be 130.992 kilonewtons. So that is the load. That is the load, the compressive, that is the load carried by the steel bars. We can also find the loads carried by the concrete, and we are going to have the load carried by the concrete will be stress in concrete times cross-sectional area of concrete. The stress in concrete is 1.112 times 10 raised to the power of 6. We multiply this by the area of concrete, which is 0.152, and this is going to give us a load in concrete, a load of 169,024 newtons. So when you convert it to kilonewtons, that is the load in concrete is going to be 169.02 kilonewtons. So ladies and gentlemen, that's how we go about this question. If it has been of benefit to you and you are yet to subscribe to our channel, please consider hitting that subscription button, and we are going to appreciate so very much. So let's meet in yet another lesson. Thank you.